Greetings. Welcome to Data Structures. Now that we're experts on sorting arrays, I want to talk about something else. Searching arrays. And what I want to do here, we have to consider a couple of different ideas here. So the first thing I want to do is I want to consider just some arbitrary array. And let's see, this particular array, 3, 4, 5. What I want to do over here is I want to have some variable here called key. And that's some number that a user specifies, and maybe it's a 17. What I want to know is I want to know, does key occur in the array? And the idea here is very simple. You could almost think of it as if I gave you a deck of cards. The cards all had numbers on it, and I just want to know, is there a card that has the number 17 on it? Now what you could do is you could come over here and you could say, well, first I'm going to look at, and let's suppose the array is called AR. So I'm going to say, look at AR of 0. And I'm going to say, does AR of 0 equal key? If yes, return 0, else continue. And then I'm going to look at AR of 1. And the same thing. I'm going to ask, does AR of 1 equal key? And the answer is, if yes, return 1, else continue. So our first attempt at this is, as well, we see we have valid indexes that go from 0 to 5. So we might say something like the following. For j equals 0, while j is less than or equal to 5, j plus plus, and I'll just say the following. If AR of j equal key, return j. Okay, now this is fine if some value gets returned. But what suppose the number we're looking for, in this case 17, doesn't occur in here? Well, then I'm never going to execute this return. And what I need to do is I need to have it return some value that indicates to me that it isn't found. Well, valid entries, if it's found, are going to be non-negative integers. So what I'll do over here is I'll just say return -1. And I'll put over here a comment, not found. Okay, so this particular piece of code here works fine. I don't like it, and in fact we're going to change it in a little bit, but this does work. If, for example, I'm looking for the number 42, this would return 3. If, on the other hand, I'm looking for the number 17, this thing is going to return a -1. And we said -1, or any negative integer, will be our indication that what we were looking for wasn't found. Now, what don't I like about this? This is purely a style issue. I don't like the fact that there are two return statements. And I think that writing methods that have two return statements in them are actually bad. Now, they don't appear so bad over here because they're only 3 lines of code. But I want you to imagine that we've written a method that might extend for 2 or 3 pages, and it has multiple return statements in it. I don't like that. I like to see one return statement in a method. I like it to be the last statement in there. So this is version 1, and this is not even a full method, but let's write a full method. So I'm going to come over here, and I'm going to say, let's consider something like this. So it's going to be public int, and I'm going to find, and I'm going to say we're searching an integer array called nums, and we'll give bounds on it. We could say start, stop, and we're looking for key. And here's what I'm going to do to make it a little bit different here. So I'm going to come over here and I'm going to say int j, and I could come over here and say something like the following. For j equals start, while j is less than or equal to stop, j++, and then I come over here, and remember, I don't like having multiple return statements, so I'm going to try something like the following. I'm going to say if nums of j is equal to key, I'm going to come over here and I'm going to say break. Okay? And now what I'm going to say down here is if well, actually, let's think about this for a second. So if I get down here, if it was found, j is going to be somewhere between start and stop. If I make it down to here, and it's not found, j is going to be bigger than stop. So if I come over here and I say if j is greater than stop, okay, and I'm going to put a comment here, not found, return -1, else return j. And I'll close that up. And I go, well, I don't know if this is a whole lot better or not. I've got this messy if statement here, and there is I've only got the break statement here. I only have I have 2 returns still. They're down at the bottom. Can I make this even cleaner? So then I wonder if people know about what's called the immediate if statement. And the way that immediate if statement works is there's a Boolean expression. And you say question mark, and then there's an expression. I'm going to call it expression 1, and then there's colon expression 2. And what happens is this thing here gets evaluated. And if this evaluates to true, we return that. And if this evaluates to false, we return that. So I could come over here and say j greater than stop. And if j is greater than stop, I'm going to say -1. Otherwise, I'm going to say j, and I put this all inside. I put parentheses around here just to make the meaning a little bit clearer. And then I could just say return this whole thing. And this statement right here could replace this one right here. But you know something? This is still messy, and I have even a better way to do it. So this is version 3. This is the one I like. So I'm going to come over here and I'm going to say int find, and I'm going to say I'm coming in with an array called nums. I'm coming in with int start. I've got int stop, and I've got int key, and I'm going to come in here and I'm going to have int j, my loop counter, and I'm going to say for j equals, and I'm going to say stop, and then I'm going to say while j is greater than or equal to start, j minus minus. So I'm going backwards. I'm starting at the end of the array and going up to the beginning. And again, I'm just going to say over here, if nums of j is equal to key, I'm going to say break. Okay, and then here's the big trick right here. I'm just going to say return j. Nothing else to it. That's the whole thing. Now let's think about it. If it finds it, okay, so if it's going to find it, it's going to find it between start and stop, and it's going to come over here, so when j is equal to some number in there where it found it, it breaks, and that's where it will return. But if it never finds it, remember what's going on here, okay? This thing over here, start, this thing's always 0. Okay, we're coming in with 0. We have an array 0, 1, 2, 3, and it keeps going like that. So what's going to happen in this situation over here, if it turns out that the number is not at 0, we're going to decrement j by 1. It's going to go to -1, and I would return a -1 here. So this works in all situations, and I think that this is actually the cleanest of all 3 of the versions that we've written here. You can go back and look at them. So a few things to say here. What is the time complexity of this? Okay, well, the worst case, well, we would have the big O of n is equal to n, where n is the number of elements in the array. I'd have to look at everything in here. And this particular algorithm here assumes the array is not sorted. And that's a key point, because we're going to talk about what would we do if the array is sorted. And this particular algorithm has a name, and it's called linear search. You should know that. So linear search assumes that we're looking for something in an array that is not sorted, and it has a worst case time complexity order n. Big O of n is equal to n. Okay, so now what we want to consider is how do we go about and how do we search a sorted array? So again, we imagine that we have an array that looks like this. And again, the metaphor that I like to look for here is as I say to people, imagine we have the Detroit phone book, and I say, find Smith, in the Detroit phone book. And if we were to think of the phone book as being this one long array, I don't think people are going to come up here and start at the beginning and go, is that Smith? And over here maybe it's AAA, and they go, no. And we come over here and we go, well, is it over here? And maybe over here we have Aardvark, and they go, no. And then we come over here and we go, is it Adams? And they go, no. In other words, the fact that the phone book is sorted means that you're not going to go ahead and do a linear search. If the Detroit phone book had 1 million names in it, and you're going to do a linear search, in the worst case, you'd have to look at all 1 million of these. And I don't think that we typically do that when we use the phone book. Now, when we use a phone book, we're going to take the phone book and we kind of open the phone book up in half. And when we open it up, there's our phone book right there. And we look over here and maybe there's Morris way up at the top here. And we say, well, it's not in this half of the phone book. So now I'm going to take this half of the phone book and I'm going to split that in half. And you'll have to pardon the crummy drawings. And by the way, when we've cut this in half, if we're assuming there are 1 million names, we've just thrown out 500,000. So now I come over here, and maybe when I cut this thing in half and I look over here and I say, well, here's Rogers. So you're going to cut this out, and now you've cut away another 250,000. And just by looking at 2 names, you've gotten it from 1 million names down to 250,000 names. Well, the same idea is going to happen over here. I've got a key. And maybe my key is 30. And the basic idea here is the following. I'm going to come down here and I'm going to have a variable called hi. Hi. And initially I'm going to set it to this number here, 4. And I'm going to have a variable low. And I'm going to set it over to this number here, 0. And then what I'm going to do is I'm going to come over here and there's going to be a variable called mid, which is equal to high plus low. And I'm going to divide it by 2. Well, 4 plus 0 is 4, and when I divide it by 2, it's 2. Okay? And it's very important that you remember that this division over here is an integer division. So now what's going to happen is if this is called AR, I'm going to come over here and I'm going to look at AR of mid. And I notice that AR of mid is 32. So my first guess at the algorithm here, what I'm going to do is follows. If this is 32 and my key is 30, what I'm going to do now is I'm now going to change high from 4 to 2. And then I'm going to repeat this whole process all over again. So what I would do then is I would now let mid equal high plus low divided by 2. So now mid would be 1. Okay? So the idea here is as follows. And by the way, what I'm describing here does have a name. It's called binary search. Okay? And what's going to happen is I'm going to call it public, that's a C, public int bin search, and I'll come in here and I'll have int AR, and I'll have int key, int, I'll call it begin, int end. And I'll come in here and I'm going to say something like the following. I'm going to say let int low equal begin. I'm going to say let int high equal end. And I'm going to have int mid. Now here's my first guess. And you should all know by now when I say first guess, there may be a problem here. I'm going to come over here and I'm going to say the following. While low is less than or equal to high, and I'm going to come over here and I'm going to say let mid equal low plus high, and I'm going to divide it by 2. And I'm going to go if AR of mid equal key, I'm going to break. Okay? And now I say something like the following. If AR of mid is greater than key, well then remember that means that key's in the first half. So what I want to do is I want to let high equal mid, else low equals mid. I make that the end of my loop. And then what I'm going to do, I'm going to be, well, remember, if I find it, it's going to come out here and break. Okay. Otherwise, I think this loop is somehow going to terminate if this turns out to be false. I'm going to try one of these fancy immediate if return statements. So I'm going to say return. I'm going to say AR mid equal key. If that's true, return mid. Otherwise, return -1. And that will be the end of my process right over there. Now, in class, I gave you this code and I sent you all home and I said there's something wrong with it, figure it out. And I think we can come over here and figure it out right here. Let me get this out of the way. Now you can see that we've partially executed this thing over here, and over here now we came back and we said, well, mid is equal to 1. Okay, so first of all, remember at this point, low is 0, high is 2, mid is 1, and I'm going to come over here and I'm going to calculate, I'm going to compare this to that. So when I compare key to mid, we can see that key is greater than it. What that's going to do is that's going to move low up to here. So now low has become 1. So now I have high is 2, low is 1. If I go ahead and I calculate mid again, well, it's going to be 2 plus 1 is 3 divided by 2. That's going to make mid 1 again. And what's going to happen is I'm going to come over here and I'm going to compare key to this, and I'm going to see that key is greater than this. And what's going to happen? It's going to assign low 1. And you're going to see that the way that this is written, this is an infinite loop. Does everyone see that? How do we fix it? It's actually really simple. I'm going to come over here and get my eraser. I'm going to erase that. I'm going to erase that. And I want you to think about the following. If AR of mid is greater than key, okay, then what I am going to do is I'm going to come over here and I'm going to say let high equal mid -1. Else, what I'm going to do is I'm going to say let low equal mid +1. Okay, And now what I want you to do is I want you to come over here and execute that again on this. We'll try and squeeze it in over here. So we had 12, 23, 32, 45, 89, 0, 1, 2, 3, 4. And let's remember what we were looking for is the key was 30. So originally low was 0, and we had that high was 4, which meant that mid was 2. So I come over here and I see that 30 is less than AR of mid. So if AR of mid is greater than key, it says let high equal mid minus 1. So now what's going to happen is I'm going to cross that out, and high is now 1. Mid minus 1. Now I'm going to come back up here. Well, low is still less than or equal to high. I'm going to recalculate mid. Well, now I'm going to go 0 plus 1. Okay, 0 plus 1 is 1, and when I divide 1 by 2, mid is now going to become 0. Everybody get that? So now when I come over here and I look at AR of mid, where AR of 0, this is a 12, okay? The key is bigger than that. So if, now what I'm going to do is low is going to be mid plus 1. So now low has become 1. Okay? Now what's going to happen is mid is going to become 1. 1 plus 1 is 2, and I divide 2 by 1, I get 1. So now I'm going to come over here, and mid is 1. Okay, low is still less than or equal to high. If AR of mid is equal to key, well, it isn't. AR of mid isn't greater than key. So now what's going to happen is low is going to become mid plus 1. So now low becomes 2. Okay, and now this is false. Does AR of mid equal key? No, it's going to return a minus 1. So now I want to consider one more example because I'm not convinced this worked. Let's suppose the key is 23. So low is equal to 0, high is equal to 4, mid is equal to 2. So it turns out that AR of mid does not equal 23, but it turns out that AR of mid is greater than the key, right? So high is going to be mid minus 1. So now high becomes 1, okay? Low plus high is 1 divided by 2. That's going to make this a 0. Okay, so I come over here, and I'm going to execute this again. And let's see, if mid is 0, that is the number 12, okay? If AR of mid is greater than key, well, it isn't. Low is going to become mid plus 1. So now low has become 1, okay? High is 1, so mid is going to become 1. And now I cycle around again. I'm still in the loop. And now what's going to happen is mid is going to become 1. AR of mid does equal key. It's going to come over here and it's going to return a 1. So this thing works, okay? And this is binary search. And again, we've discussed this in class. What is the complexity of this in the worst case? Well, what happens is we keep cutting the array in half, and we keep cutting it in half until we get down to just one element. And the question is how many times do we keep cutting it in half? And the answer to that is log n times. So the complexity of binary search is log n, but this assumes a sorted array. And that is the big difference between binary search and linear search.